Okay, welcome to the review sheet for Chapter 11, the unsaturated hydrocarbons. I recognize this as Chapter 12, but it's Chapter 11. Chapter 11 talks about these unsaturated hydrocarbons. Now, actually, before we get into that, I want to remind students that these review sheets are not meant to replace lecture. They do not cover everything that we talk about in lecture, and they certainly don't cover it in the detail that we do in lecture. So it's a good review, an overview. It covers a lot of things that you'll find on a test, some of the most important concepts, but a lot of the details I won't be getting into, so just be warned. Alright, unsaturated hydrocarbons, there's three main types. We have alkenes, alkynes, and aromatics. There's this term aliphatic here. What does aliphatic mean? Aliphatic actually comes from the term slight affinity, and essentially what this means is the term originally meant that they had like slight affinity with water, so they're non-soluble, right? They're non-polar. They don't dissolve in water. What it really means now is simply the saturated alkanes, and we really just talked about two types. We had there's a plain ordinary alkanes, and then the I should say not saturated alkanes, but saturated hydrocarbons. Let me clean that off. Saturated hydrocarbons, of which we had really two types. There were the alkanes, and then I'm going to put a little squiggly here, cycloalkanes. Really, cycloalkanes are unsaturated, but for the purposes here, we can consider them aliphatic. The book also, I think, uses two terms. They're cyclic and acyclic. Alkanes are acyclic, right? In other words, there's no circle, there's no ring structure, whereas cycloalkanes had the rings. Alright, alkenes have the carbon-carbon double bond. It doesn't really have a functional group, but so I'm just going to put here carbon-carbon double bond. Alkynes, this is pronounced alkynes, K-I-N-E-S if you wish, kynes, and it has a carbon-carbon triple bond. Aromatics have aromatics are derivatives of benzene. If you remember, there's a few ways of drawing benzene. Benzene has a chemical formula C6H6, and we'll get more into the structure of benzene later, but it's this cyclohexane ring with three double bonds in it, or sometimes you'll also see it as a hexagon with a circle in it. That circle represents those double bonds. All right. Given the structure with IUPAC names for these unsaturated hydrocarbons, essentially you're going to apply the same IUPAC rules that we had in chapter chapter 10. Okay, but we're going to end these compounds in a different suffix. So alkenes will end in -ene. They have the -ene ending. Alkynes end in -ine. Well, one of the things about alkenes, the general formula of an alkene with only one double bond is CnH2n. So let's look at the simplest alkene here. Right? Now this is ethane. It's an alkane. It has a carbon-carbon single bond. The simplest alkene right, this would be ethyne. This is ethene. Right, it's an alkene, has a double bond, ends in -ene. And if you look at the chemical formula, if you look at the chemical formula, it is C2H4, whereas ethane is C2H6. Remember, for alkanes, the general formula is CnH2n plus 2. We also had cycloalkanes. These were not isomers of the alkane, so hexane is not an isomer of cyclohexane because these have the formula CnH2n. Well, that's what you see down here for ethane. It's C2H4. The general formula here is CnH2n, similar to the cycloalkanes. In essence, you lose the +2 part. What you've done here is essentially remove 2 hydrogens to go from ethane to ethene. Okay. The rules for naming these, let's just real quick. I'm not going to draw the whole structure, but we have something like this. This would be 1-butene. We indicate where the double bond is with a number. This 1 here indicates where that carbon-carbon double bond is. It's between carbons 1 and 2. We could also have 2-butene, right? This now has a carbon-carbon bond, 2-butene ENE. This 2-butene has a double bond between carbons 2 and 3, of course. A double bond is going to exist between 2 carbons, but if it's between 1 and 2, we choose the smaller number, so it's 1-butene. If it's between carbons 2 and 3, we choose the smaller number 2, so 2-butene. Again, 2 indicates where the double bond is. Okay, be able to identify cis-trans isomers from given structures. If you remember, cis-trans applied to cycloalkanes. We saw this with cycloalkanes. So put here cycloalkanes, right? Where we could have 2 groups maybe on the same side of the ring or on opposite sides of the ring. Similar kind of thing happens here with carbon-carbon double bonds only, not the triple bonds. So cycloalkanes and alkenes. I'll put here not alkynes, the hydrocarbon with the triple bond, not alkynes, but with alkenes. So cycloalkanes and alkenes. Cis means same side. Right. Trans is opposite. So just to review, if we have a cycloalkane, make this a little bit like this. Okay, we can have 2 groups that are, say, on the same side. We'll put 2 methyl groups down here. Okay, so this would be cis-1,2 dimethyl-cyclohexane. So cis means same side. Similar kind of thing happens. If you recall, when I talked about cis-trans here, I said, well, once you form a ring, these carbons are bonded such that they can't rotate. Similar kind of thing happens in a carbon-carbon double bond. In a carbon-carbon double bond, you cannot rotate about that double bond. And so if you have 2 groups on here, let's put a hydrogen here, and a CH3 there, and a CH3 down here, and a hydrogen up here. This is cis-2-butene. 2-butene. Why is it cis? Well, the 2 methyl groups are on the same side, or if you wish, the 2 hydrogens are on the same side. It doesn't matter which way you look at it. Why is it 2-butene? Why isn't it an ethene? Well, you find the longest continuous chain. That's 1, 2, 3, 4 carbons. So the way we've drawn it, it may look like these guys are branches, but they're not. They're part of the main chain. You can go from a carbon through a bond, right, to another carbon through a bond, to another carbon through a bond. So we have 4 carbons in the chain. That double bond is between carbons 2 and 3, so we say 2-butene. So this is cis-2-butene, and there's a trans-2-butene. These guys are isomers. They're going to have different shapes, different names, different properties, but what they share is the same chemical formula. This is trans-2-butene. And caution, it says, note here, not all alkenes have cis-trans isomers. In order for there to be cis-trans isomers to exist, there must be what? You must have 2 the technical term scientists use is something called a moiety. I'm just going to say two things. You've got two things that are the same on the carbons that are joined by the double bond. So we have two methyl groups if we wish, two CH3s that are the same, or if you wish, two hydrogens that are the same. So let me give you an example of alkene where we do not have two things that are the same, in which we cannot use cis and trans. Okay, this guy here does not exist cis trans isomers, and you're saying to yourself, well, wait a second, there's two things that are the same. We've got a hydrogen here and a hydrogen here, so they're the same and they're trans, right? Well, yeah, but we have a hydrogen here and a hydrogen here, and they're on the same side, so they're cis. So what is this, cis or trans? It's really neither. You can't, I mean, there is no cis trans or geometric isomer of this compound. What is the name of this? Well, we've got 1, 2, 3, 4 carbons in a row. The double bonds between carbons 1 and 2. So this is 1-butene, and there is no cis trans. It's simply 1-butene. No cis trans isomers exist for this. So what you're looking for is in order for cis trans to exist, you're looking for two things that are the same, right? They have to be on opposite sides, but you can't have how should I say? You can't have, if we look at 1-butene, the hydrogen and hydrogen here, all right, those are the same. Well, they're the same atom and they're on opposite sides, but you can't have the two things on the same carbon either, right? The hydrogen on that one, hydrogen here, that's not going to be. If these two are the same, you can't have cis trans. So I'll give you another example. Let's say we have. Might run out of room here. Doesn't have to be a hydrogen. Okay, so it could be something like this. Right? We have a methyl group on one side, a methyl group on the other, so they're trans. No, we have a methyl group on the bottom, methyl group on the bottom, so they're cis. What is it? It's neither. It's neither cis nor trans. It is simply, well, let's see, what's the name of this? We've got 1, 2, 3, 4 carbons in a row. 1, 2, 3, 4 carbons. So it's a butene, right? We're going to end in ene because it's an alkene. It's 2-butene. We've got the double bond between carbons 1, 2, and 3, so we're going to say 2-butene. We also have a methyl group on carbon 2. So let me outline the main chain here. Right? So that's the 2-butene. Right? That's our 2-butene. We also have a methyl group on carbon 2, so this is 2-methyl 2-butene. And again, no cis trans for either one of these guys. All right. Be able to identify addition reactions and complete addition reactions given the starting reactants. Hydrogenation, where the word here has got hydrogen in it. Right? So hydrogenation is addition of hydrogen. That means one of the reactants, I'm going to put here plus E, is elemental hydrogen. So another question here, what is meant by unsaturated hydrocarbon? Well, if we look at one of these reactions, let me go ahead and draw simple. Actually, I'm going to change that. Let me change this a little bit so we can see the hydrogens a little bit more clearly. All right, what's the name of this? 1, 2, 3, 4. There's 4 carbons in a row. That's 2-butene. And we have 2 methyls on it, so it would be 2,3-dimethyl 2-butene. I won't bother writing that name down, but 2,3-dimethyl 2-butene. Write it down if you wish. What I want to show you here is if we add hydrogen, and these reactions, by the way, are usually catalyzed by some fancy metal like platinum or rhenium or palladium. This thing we put in the reaction arrow is a catalyst. Okay, we saw the use of a catalyst that was at aluminum chloride in that was at hydrocarbon lab. Right, we used the catalyst. If bromine didn't add across that double bond, we added a catalyst to see if we could get it to go, and the aromatic hydrocarbon, the toluene in that lab, should have reacted once you added aluminum chloride, which was the catalyst here. The catalyst is platinum, which speeds up this reaction, gets it to go. Well, what happens here now? In all of these addition reactions, that double bond disappears. It becomes a single bond. And the hydrogens are added across that double bond. So we've got a double bond, becomes a single bond, and the hydrogen, which is H2, just splits up and is added across that double bond. Now this compound, it's an alkene, and we say it's unsaturated. Right? What is meant by an unsaturated hydrocarbon? We've got either a carbon-carbon double bond or a carbon-carbon triple bond. Okay? And then we can add hydrogen to it, and it kind of soaks up or absorbs that hydrogen. So what is meant by unsaturated? It's unsaturated with respect to hydrogen. You might be familiar with the term unsaturated with respect to solutions. Right? An unsaturated solution is, say if you have a salt solution and it's unsaturated, what does that mean? It means you can add more salt to that solution. Well, these are unsaturated hydrocarbons. You can add more hydrogen. So what is meant by unsaturated? In essence, it means you have a double bond or a triple bond, but where that name comes from, I just say comes from the fact that more hydrogen can be added. Okay. Halogenations. Halogenation is the addition of a halogen. The halogens are fluorine, chlorine, bromine, Br2, or iodine. So again, using, well, I'm going to make a little bit simpler hydrocarbon here. We can use maybe 2-butene again. What is this? Is this cis or trans 2-butene? Right, they're on the same side. This is cis 2-butene. If we react this with, let's say, iodine, what happens? Well, in a similar fashion, where we added the hydrogen across the double bond became a single bond, and each carbon that had the double bond gets a hydrogen. Similar thing happens here, except of course we're adding iodine, so each carbon will get an iodine. So these two carbons here, that's these two that had the double bond, now it's a single bond, and CH3, and the iodine goes on the top. Whoops, I forgot the hydrogens, right? Each one of these had a hydrogen as well. All right, so make sure these carbons each have 4 bonds. So we just add iodine across that double bond. In the laboratory, we did this not with iodine, but with bromine. Right? Now, if you remember, bromine was a kind of a brownish, dark red, brownish sort of liquid. And when it added across that double bond, the bromine molecule didn't exist anymore. It was converted to the 1,2-dibromo, or actually in this case it would be 2,3-dibromo, or 2,3-iodo, I guess. But the brown color disappeared because the bromine got used up. Right. Hydrohalogenation. Hydrohalogenation is the addition of both a hydrogen and a halogen. Actually, I should use different colors here. Let's use red for the hydrogen and the blue for the halogen. So this time let's use bromine. Right. So one carbon, we're going to do the same thing. One carbon is going to get the hydrogen, the other carbon gets the bromine. I'm not going to bother drawing the structure again, but I'll just say, okay, we're going to add, what, HBr. So we're adding a halo acid, we're adding hydrobromic acid. Right? Starting with the same starting material here, what are we going to get? Well, a hydrogen is going to go to one carbon. Right, there's our hydrogens in. Okay, this bond here, that was our double bond. Right, was our double bond, becomes a single bond. One carbon gets the hydrogen, the other carbon gets the halogen, and so this reaction, called a hydrohalogenation for reasons I won't get into, is a hydrohalogenation, not a halohydrogenation. It's a hydrohalogenation. The hydrogen comes first, if you wish, in the HBr, so hydrohalogenation. In the textbook, they talk about Markovnikov's rule. Right? Markovnikov's rule governs whether, the hydrogen or the carbon on the left gets the hydrogen or the carbon on the right gets the hydrogen. And I told you in lecture, do not worry about Markovnikov's rule. It's not something that we need to go into at this level. So, all right, last one, hydration. Hydration, when you hydrate something, I don't know, maybe you have some dried noodles or peas or something at home. What do? You hydrate it, you add water. Now, for the purposes of this reaction, let's think of water as HOH. Right? So it's hydrogen hydroxide. If we add water across a double bond, okay, we can... these reactions are also catalyzed by an acid, maybe sulfuric acid. Generally, it would be sulfuric acid. You don't want to use a halo acid for this, for reasons I won't get into. So we'll just put a hydrogen ion on the reaction arrow, meaning that this is catalyzed by a general acid, usually sulfuric acid. Let's draw that double bond disappears. We get a single bond. And a hydrogen is added to one carbon and an OH to the other. Again, Markovnikov's rule would apply here. So if you're reading the book, they might tell you, oh, the hydrogen's got to go to this carbon or that carbon. Don't worry about it. I'm not going to hold you to that. But what you should recognize is this is an alkene, right? It's got a double bond. This was chapter 11. This takes us to chapter 12. Chapter 12 is on alcohols. So if you remember, going up here, if we add hydrogen, we go from an alkene. This is an alkane. So make note of what's happening here. We change the alkene, which is unsaturated, to an alkane, which is saturated. You cannot add any more hydrogen to an alkane, so it is saturated with respect to hydrogen. Halogenation, we get a halogen to it. We get a 1,2 dihalide. I shouldn't say 1,2. In this case, 2,3 dihalide. They're on adjacent carbons. If hydrohalogenation, we just get one halogen added. Again, we're adding a hydrogen here, but you can't tell that doesn't really change the nature of the molecule by adding a hydrogen here, but you get this alkyl halide, just one bromine is added, right? There's one bromine here, one bromine on this carbon. Here we go from an alkene to an alcohol. And that is the next chapter in line here. That's chapter 12. We'll talk about alcohols. All right, next in line. Be able to identify and name aromatic compounds. Remember, aromatic refers to the fact that these guys, it used to mean that aromatic compounds, they thought they all had an odor to them, and many do, but not all. Aromatic compound really now it just means it's a derivative of benzene. Okay, so what does aromatic mean? You've got this ring structure, a hexagon with the ring in the middle. So these are all derivatives of benzene. So diagram resonance structures of benzene. I won't go into all the different how we convert one to another. But what I want to point out here is, let's make this, put a CH3 on the top so we can kind of keep our orientation. Okay. What I want you to recognize is that we are not rotating the molecule, right? The CH3 is still at the top. But if you look at it in one instance in time, the double bond is between these two on the left, and now the next time maybe it's moved over here, and this guy is moved down here, and this one is moved here. So it looks like the double bonds have moved. And really, this happens so quickly, we can't distinguish one from the other. And just like a violin string, at rest you can say, okay, I can see the violin string. When you pluck that violin string, it looks like it gets wider. You know it's vibrating from one side to the other, but it's going so fast it just blurs out. And that's why we get this shorthand structure for benzene with this circle in the middle. The circle in the middle, if you wish, what does the circle in the middle represent? It kind of represents this smeared out, or what we call delocalized electrons. So these double bonds, I'm going to put them as dashed lines. They're kind of smeared out, or they're resonating, right? So we call this resonance structures. They're smeared out throughout the whole molecule. So the circle in the middle represents delocalized electrons. Why do I call them delocalized? Well, if we look at the static, these are also called Kekulé structures. I don't know if the book uses that. These are Kekulé structures, and they are not the best way to look at it. The best way is something that we call a resonance hybrid. This is referred to as a resonance hybrid. Okay. The double bond, let's just take this double bond here, right? This blue guy. In the resonance hybrid, it's not just stuck between this atom and this atom. Let me go ahead and just put little hydrogens. Remember, there's hydrogen in each corner here. It's not stuck between these two. It's actually smeared out. So that's why we draw these dotted lines. It's not localized between any two atoms. These are delocalized. They're kind of spinning around. Maybe another way to think about this are the blades of a fan, right? When the fan is turned off, you can see the blades, but when you turn it on, it's spinning so fast, you don't see the individual blades, but the blades become a disc, and they're delocalized, right? So they're spinning around. That's one way to think about it. Now then, there are certain derivatives of benzene that I want you to know, and this is just something you have to kind of memorize. But benzoic acid is an acid, and if you remember back in the last chapter, we talked about the acid functional group, the carboxyl group. This is a carboxyl group attached to benzenes, hence it is benzoic acid. Phenol is a little bit different. Phenol, right, we've got a benzene ring, and we have an OH. Phenols end in OL, like all alcohols. So this is the alcohol group, the hydroxy group, right? That's what makes this a phenol, and it ends in OL, just like an alcohol does. Toluene, that was that compound up above that I drew in red. Toluene has a methyl group attached. Aniline, this is pronounced aniline, not aniline. I know there's an E on the end, but nevertheless people pronounce this as aniline, has an amino group on the end, attached to the ring. And lastly here, naphthalene. Naphthalene is one of these polycyclic aromatics. We have two of these guys bonded together. They're fused together. That's naphthalene. Okay? It's not this. This is aromatic as well. We're going to have two benzene rings, but they do not share a common atom. Okay? This is something called a biphenyl. Now notice there's a similarity between phenol, which has the OL, and phenyl, which has a YL. Okay? So remember if we had methane, well, we talked about alkyl groups. Right? Remember, we talked about alkyl groups. So methane was a 1-carbon alkane. If it was a branch, if we named it as a branch, we changed the ending from methane to methyl. Right? Well, here we're naming these benzene as essentially a branch, and so they're called phenyl. Why are they not called benzyl? I'm not gonna. Don't blame me. I'm not responsible for that. But a benzene ring named as a branch. Okay, this is called a phenyl group. Okay. All right. Name aromatic compounds using orthometapara designations. Orthometapara. This is first off. This is only for di-substituted benzenes or di-substituted aromatic compounds. What do we mean by di-substituted? Di means two. We've got two things attached to the ring. Ortho means they're right next to each other in 1, 2, carbons 1 and 2. Meta, it's kind of the middle position, 1, 3. And para, they're across the ring from each other, 1 and 4. So ortho could be like this. This is ortho dimethyl benzene. I'm just going to put O here for ortho. Ortho dimethyl benzene. Notice up above we talked about toluene as having a methyl group. Now we can't name this a toluene because it has 2 methyl groups. So there's actually another name for this. It's called a xylene, but I'm not going to ask you to know that. So we would call it instead dimethyl benzene. Meta. Meta, these are the middle positions. So we'll put maybe something on here like this. This would be meta what? Well, B comes before M, right? Bromomethyl. So we're going to number this like that. If we were to name this using numbers, it would be 1 bromo, 3 methyl. Okay? Or you could simply name it meta. So these compounds have a variety of different names, but this would be meta bromotoluene. Now here we can name it a toluene because there's just 1 methyl group attached. So meta bromotoluene. It says you have a toluene and the bromo is in the meta position. Do one more. Okay. All right, that's phenol. And I'm going to put a methyl group here. So we could name this as a phenol, right? The methyl group is para to it. These guys would be in 1, 2, 3, 4. So you could call this, if you're using numbers, you could call this 4-methyl phenol. Right? Carbon number 1 has got the alcohol group, so it's phenol. Or you could simply say para methylphenol. And if you're asking yourself, wait a second, self, if it's got 1 methyl group, it isn't a toluene? Couldn't I call it like 4 or para-hydroxytoluene? Actually, this compound again goes by a common name called a cresol. So this would be para-cresol, but for purposes of just explaining what orthometapara means, these guys are across the ring from each other in positions 1 and 4. So paramethylphenol, if we were using numbers, it would be 4-methyl phenol. Okay. Why don't aromatic compounds have cis-trans isomers? After all, they've got all those double bonds, right? Well, the thing about benzene, and for reasons I won't get into, benzene is a flat molecule. You'll talk about this in the text, and they talk about it. They talk about hybrid orbitals and whatnot, and these are all sp2 hybrid carbons. Oh, I need a circle in the middle here, don't I? So it's a flat molecule. All the atoms are in the same plane. So these two methyl groups, there isn't a top side and a bottom side of the ring. They're all in the same plane. So benzene is planar. That is flat. There is no top or bottom side to the ring like we had with cycloalkanes. We've got all those double bonds, but the other thing to consider here is you've got just hydrogens. You don't have two things attached to each carbon. You only have one. So it's planar flat. There's no top or bottom side, so you can't think of it as cis-trans like with the cycloalkanes. And I'll say, and only one atom. I'll put here these hydrogens in this picture, guys. In this picture, only one atom attached to each carbon. Now, obviously, the carbons in this ring, I mean, they're attached to two carbons, one on the top, say one on the bottom here. What I'm talking about are the guys that are on the outside. So if I had, like here, these two methyl groups, right? That's what I mean, is the one methyl group on this carbon, one methyl group on that carbon. And if you recall, for alkenes, you needed two things. Let's just draw an alkene here real quick. You needed two things attached. Right? So we could say, oh, there's a hydrogen and a methyl. Here there's only hydrogen, so there's no cis-trans. Number 8, why are these aromatic compounds stable? Why don't they undergo reactions like alkenes? After all, they've got all these carbon-carbon double bonds. Well, that's because they're not really true carbon-carbon double bonds. If you remember, let's see if I can draw this kind of big. All right. Those double bonds are not true double bonds. It's as if they're a bond and a half. They're smeared out. Okay. So I'm just going to say no true double bonds. In fact, all the bonds in benzene are the same. They're each, if you wish, a 1.5 bond. No true double bonds. All bonds in a benzene ring are the same. We don't have, there are no double, although, you know, in the Kekulé structure we draw a double bond and a single bond and a double bond and a single bond. There are no double bonds. So likewise, no single bonds. Okay, instead they're really more like a bond and a half, and those 1.5 bonds, if you wish, do not undergo addition. Okay. Lastly, name compounds using the phenyl group nomenclature. If you remember, the benzene ring named as a branch is a phenyl. So benzene is C6H6, right? A phenyl ring would be C6H5. Why do we need to worry about this? Well, let's say we've got some great big crazy thing here. Right. You've got a benzene ring, okay? All right, well, what's the name of this thing attached to the benzene ring? There is no name for something like this. So instead, what do? Well, we find the longest continuous chain. I'm going to go up or down. Let's go up. The longest continuous chain, anything sticking out of that box is a branch. We've got a bromo, we got a phenyl, and we got a methyl. Right? B is first, then M for methyl, and then finally P for phenyl. So we're going to start at this numbering here. This is 1, 2, 3, 4, 5. So this is a pentane. Right. On carbon 2, there's a bromo, so it's 2 bromo. 4-methyl, right? Because M comes before P in the alphabet, and then finally 3-phenyl. Squeeze that in there. You can't really read that. 3-phenyl pentane. So that's why we need to know about this phenyl group. One other thing I'll mention, this is the Greek letter phi, and sometimes phi is used to indicate a phenyl ring. So if you ever see something attached and it looks like this squiggly thing is a circle with the line through it, that's the Greek letter phi. Phi stands for phenyl. Okay. All right. So again, remember, I went through this quickly. There's a lot more detail in your chapter and in the notes. So look over your notes. Look over this. This distills the chapter down fairly well. Covers most of what we talked about in chapter 11, but by no means is this all you need to know. Thank you.